next speaker is Kevin, who will tell us about learning as a tool for algorithm design and beyond worst case analysis.
So yeah, I decided in the title of this talk to riff on the title of the workshop, because after all, it seemed to actually give kind of a good outline for what I wanted to talk about. And I promise I actually had no impact on the title of the workshop. This is just a happy coincidence. The nature of this talk is going to be to survey a lot of work that I've done with a lot of different people, all at a pretty high level. My sense is that this audience will be more interested in hearing about the sort of high-level structural takeaways from things that we've done than walking carefully through some piece of experimental analysis. So at the beginning of every section, I'm just going to have some sort of call-outs to various papers to kind of give due credit to my co-authors. In particular, let me note some co-authors who appear sort of throughout the talk, and particularly among them, Holger Huus, who's here. So the motivating problem that I want to think about in this work is thinking about how solving NP-complete problems works out in practice. And if you look at an algorithms textbook, for example, Hopcroft, Motwani, and Ullman, you'll hear that your problems are intractable when they can be solved, but not fast enough for the solution to be usable. And we often hear about NP-complete problems being intractable. In reality, if that's what we mean by intractable, then the reality is more complex, because there exists this whole literature in AI on trying to find good algorithms for solving NP-complete problems. And although the best available methods don't offer interesting theoretical guarantees, which might be where I lose all of you, it's nevertheless the case that these algorithms work just astoundingly well in practice. They work really reliably well in practice, as we've heard from some of the previous talks. Nevertheless, if we look under the hood, they also tend to exhibit exponentially varying performance. So even when we hold size constant, we can see runtimes that on problem distributions that we care about that range from milliseconds to days. So there's clearly something structural going on that is interesting to understand and necessary to understand. But on the other hand, there's also clearly, it would be the wrong thing to just dismiss these problems as being unsolvable. So the question that will motivate this talk, and that has motivated the research going into this talk, is asking how hard is it to solve a given problem in practice using the best available methods? And this is tricky because the best available methods are typically really not amenable to analysis. They don't tend to offer theoretical guarantees that we can do anything useful with. And in fact, we can't even necessarily take them apart. We can't even necessarily look at something like Cplex and know how it works. It might be, in fact, a trade secret how the algorithm works. We only get sort of black box access to it. The upshot of this work that I want to kind of leave you with is even in such crazy cases where formal analysis seems hopeless because I can't even look at the algorithm, the instance distribution I want to look at is, again, not analytically described, but maybe given to me only by samples. It's possible to take a statistical view in which we can answer such questions with high levels of statistical confidence. And I guess Holger's talk yesterday, thinking about a very different problem of scaling behavior, gave another sort of sense of what that might look like, to try to give statistical guarantees about problems that are difficult to think about analytically. So the kind of core idea, that the learning in the title of my talk here, is the idea of what we call an empirical hardness model. And the idea of an empirical hardness model is to essentially treat an algorithm analysis as a natural science problem. To say, I've got this black box algorithm. I don't really know what it does inside, but I can run it on problems that I care about and measure its runtime and observe what happened. And let me then try to think about the problem of analysis as being able to predict what it's going to do on inputs that I haven't yet given it. So I can set this whole thing up as a machine learning problem. I can say, let me get some given set of distances, a given distribution of instances sampled from some instance distribution, so some set. Then for each of these instances, I can compute some set of features, which is going to be some real vector of different measurements about the instance that can be done in sort of low order polynomial time. And then I can actually run my algorithm and label this instance with a runtime observation. So yeah.
So there's a hidden assumption here, or not hidden, kind of implicit assumption that the instances are coming from a fixed stationary distribution.
That's indeed not hidden. I'm trying to be quite upfront about that, but that's exactly the setting I want to think about. So if I'm going to do something statistical, I'm not going to be able to speak about how my instances do, in some totally different setting that I have no data to describe. So instead, I want to speak about a distribution, absolutely.
But this is in contrast, say, for the online setup, in which you don't assume such a stationary underlying generation of instances.
Absolutely, yes. So here I really want to think about there being some, you could imagine if I cared about online settings, each setting might be a sample and I could see many such settings, but I want my instances in some sense to be IID. And indeed, not every algorithm design problem looks like this, but I would argue that many do. And if you find yourself in one of these problems, then really you face a supervised learning problem. There's now kind of a regression problem that says, I want to find a mapping from whatever it is that I can measure about each instance cheaply to the runtime of my algorithm. So if any such mapping is a kind of prediction that can be made about every new instance that I see, saying how long that algorithm will take to run. So that's what I'm going to call an empirical hardness model. It's such a mapping. And the question is it possible to do this at all? Like, does it even make sense to think that you could do this for an NP-complete problem? And how well does this work, and how robustly does this work? So that's the first question that I want to investigate. If you're a machine learning type, you might immediately sort of latch on to the fact that I'm talking about different approaches to regression and think, what sexy regression method are you using? Are you using Gaussian processes or deep learning or what have you? We've tried, over the years, a whole variety of different methods. I think our kind of high-level message is that it makes a bit of a difference which method you use, but it's not really a story about methods. The features are more important, as is often the case in machine learning. And I'll speak about the feature. I'll finish my sentence. I'll speak about the features more in a moment, but most of what I'll speak about today will concern random forest subregression trees, which are a robust class of machine learning models, which has the advantage that it deals very nicely with discontinuities, which turns out to be important in this domain. Yeah.
Can you say a little bit about how you discover these features? I mean,
I'll say a bit about it at the end. What I'll say now is that mostly, we'll look at the theory literature. We'll look at the kinds of quantities that turn out to matter in parameterized complexity analyses or in various kinds of proofs that people make about these kinds of problems. What are things that I could cheaply measure? Like what kind of graph can I compute based on this instance? And then what structural properties of the graph might be interesting? Or what relaxations exist for the problem? And what can I measure about the solution to the relaxation? Things like that. And I'll be more concrete at the end. But I'll say that typically what we've done is spend a week kind of just combing the literature for sort of everything, get an exhaustive list of features, and then rely on machine learning methods that can throw away unnecessary features. And typically that's worked very well for us. So we haven't found that we need to very carefully engineer this set of features. At least nothing that I'll show you has depended on that kind of engineering. Any other questions? I'm, by the way, very happy to be interrupted during the talk, so please don't hold yourselves back.
So F is some kind of problem that we are trying to solve?
No, so each X is a problem that we're trying to solve.
And F is say, independent set?
No, so F is a learned model. So each X is so basically what I'm interested in is these instances, and then for each instance I, I'm going to measure some properties of that instance. And what I want to do is this distribution of instances might all be independent set problems or SAT problems or whatever they are. I'm going to generate the constraint graph and do whatever things I do to get my vector of features. And then I'm going to try to find a machine learning model that, given those features, predicts how long such a problem would take to run.
So, maybe for this, xi are the I index are the coordinates of x, are the feature coordinates of x, or the I is the instance? I mean,
So the I is the instance, the X is the name I'm giving to the vector corresponding to that
it
instance.
looks like for every instance you use different features. Because you say for each instance, I choose a different feature.
Well, I've got to actually be able to compute these features, so I will have a different vector for every instance. So the first element in the vector might be what is the average degree in the constraint graph corresponding to that instance. It's the same dimensionality.
It's the same features, but different
Different such values, yes. But think of it as a constant dimensional vector. Okay. So here's kind of an overall summary of what we found in maybe 15 years of experimentation on this sort of family of problems. We basically, the upshot, I wouldn't be standing here talking to you today if it wasn't the case that we found that these methods work really reliably across a really broad range of instances. And indeed, we started out doing this with a really not very ambitious goal of tuning an instance generator for combinatorial auctions. And we thought this was going to be terrible, but maybe good enough that it would correlate with something. And we became really surprised by how well it worked. And this led us down the garden path of thinking more and more deeply about this problem. So now we've thought a lot about satisfiability, mixed integer programming, traveling salesman problem, and combinatorial auctions, which is where we began. We've looked at dozens of different solvers, including black box commercial solvers, state-of-the-art solvers everywhere, and many dozens of instance distributions looking at benchmarks proposed by other people, various real-world data. So really our goal is to think about hard problems and both instance distributions and solvers that there's some kind of external reason to care about. And here's some, I could show you graphs and dig into the analysis for my whole talk, which I'm not going to do. But here are some examples of what results look like for us. So at the top here, I'm showing you two different distributions on SAT. And on the bottom here, I'm showing you two different distributions for mixed integer programming. And let me walk you through what each of these things means. So on the x-axis here, I've got the actual runtime. So first of all, before I even show you this, I should say what we do is we gather a whole bunch of data in the way that I described to you. We label that data by actually running our algorithm on each of these instances. We get a training set. Then we have another set of instances, which we've randomly partitioned from the data that we were given, which we also gather runtime observations on, but which we set aside as a test set. And all of the results that I'm showing you here are evaluations of the model trained on the training set, evaluated on the test set. So in every one of these cases, the model only gets to observe the feature values for some instance that it never actually got to see in training. And then we see how well the prediction of the model matches up against the actual thing that happened. And so every one of these dots in the graph corresponds to such a run of test data. Yeah?
So to get enough data, maybe you have a generative model, or are these real-life instances?
There are, it differs. I think maybe all of these are real-life instances, okay. But we've certainly also sometimes worked with generators.
But with generative models, you would expect that there's a small number of parameters that sort of give away what's going on. But it's interesting that
you might. I think if you push harder on that, it's not always the case that the things you're measuring about the algorithm line up very well with those parameters. But indeed that might be. I mean, as it happens, the 4 examples I've got here are every problem that was ever entered in a SAT competition through all of the different tracks is that graph. This is real problems from hardware verification with a particular SAT solver. This is something on protecting habitat for red-crested woodpeckers solved with CPLEX and encoded as MIPS. And this is all of MIPLib, which was this wildly heterogeneous library of MIP data that the MIP community has assembled. So all of these are data sets that came from, that don't have some clean analytic generating process. Yeah.
Are they all the same size, or is this also, okay.
Not at all. I mean, something like MIPLib, for example, there's wild variation in size, as there is in the SAT competition. I mean, I think the SAT competition problems vary from being maybe a few K to like 500 megabytes as the size of the input instance. They're really wildly different in size.
So what can be slow is both time and complexity for a given instance. Like, an instance can be hard or an instance can be big, and both of those things would like.
Sometimes the big instances are really easy.
Sure.
Sure. Yeah, there's not size is not necessarily a monotonic predictor of hardness in these crazy heterogeneous distributions. Yeah.
So each of these graphs is for a fixed algorithm. for a fixed solver.
Yes, each of these is for a given solver,
Now,
absolutely.
if you want to use it in order to learn how to pick a solver.
That's on my next slide, so let me defer. Let's right now think about this question of one solver. Because I think it's still quite surprising that you could say something about what Cplex is going to do. I mean, even if I fix one particular Cplex, I think that, to me, that was quite a surprising thing already. And so I just want to continue kind of walking you through what these graphs mean. So what we would want to see is all of the points on the line. Well, I guess what I haven't said yet is that here I'm looking at runtimes varying on a log scale, right? So this is a runtime that took 10 to the minus 3 seconds, which is like a millisecond. This is 10 to the 4 seconds, which is like a day or something. So we have really, really enormous runtime variation on these plots. And what we would like to see is all of the points lined up exactly along the blue line. That would mean I made a runtime prediction, and then here's my prediction, and it was exactly whatever the actual algorithm runtime was. If I look at how much they vary along this plot, that's just telling me the actual variation in runtimes that I had in that distribution. Yeah.
So are the vertical dots, there's some artifact-looking things, a vertical dot,
Yeah, those are cutoffs.
Okay.
So it wasn't possible for us to run, I said that's a day. I don't know if it's actually a day or if it's like half a day or something, but each of these points is incredibly expensive to compute, right? I have to spend an actual many, many hours on a computer cluster just to get that one point. And so, at some point we just have to stop. And so, in fact, there's a machine learning question there, which is how do you build unbiased models from censored data? We've actually written a couple of papers about that because that's pretty important in this context. I'm not going to get into the details, but you will notice that the data is censored, and that's not a mistake.
No, but the downward line, that's actually where the prediction was.
so you just cut off the
A horizontal line would be a constant prediction.
Would be
Right, so this is a censorship in measurement that really these would have gone further out. Something else you'll notice if you have a really good eye is some striping here on the left side, and that's resolution of the CPU timer when we get into very small runtimes. So that's a different kind of measurement error.
The vertical line on the left, that's grossly underestimated, right?
So the vertical line on the left, are you talking?
On the right.
Yes. So this is a case where the runtime is something much larger, and all we're observing is a bound on the runtime.
And your estimate was somewhere quite low.
Yes, and so here, in this particular case, we're using random forest models which don't extrapolate, so they can never give a larger value than they've seen. So we would never go above this point because there's nothing in the data that's bigger than that point, so we can only expect that there's stuff here and below. And in a scatter plot, you don't see density well, so you don't have a good sense of what a large fraction of our stuff is there versus there. So, but if we look at the root mean squared error, which is actually pretty small in this example, it gives us a sense that our eye is being misled by this line, and it's not as big as it looks like it is. But so, broadly speaking, and I should say these are some pretty challenging problems because, in particular, both of these ones are really heterogeneous. They're sets of problem distributions, of sort of dozens of problem distributions, which in training data are pretty sparsely sampled. And so that's why we see bigger variation here. That maybe doesn't surprise us so much. In this column, we're looking at something that looks more like the problem a practitioner would have of studying one domain and seeing how it works well. I should say this is one of the best results we've ever seen. This isn't typical, but this kind of result is typical. So we really do tend to see just pretty accurately predicted runtimes, even across really wide variation. And I guess what I want to leave you with is the notion that this is possible to do, subject to some error. Yeah.
This is Cplex with one. All these dots correspond to the same setting of.
Yes, this is Cplex, running on its default setting. So we just take the MIP, throw it at Cplex, and see how long it took. Okay, but you guys are clamoring for more settings, so let's talk about that. So here I've been talking about black box algorithms, but you can then, as many people have been doing at this workshop, think about parameterized algorithm families. And so here we can basically say I've got my features that describe the instance, and I've also got the algorithm parameters. And let me now build a model in both of those things. Because we're doing this in a statistical way, we're going to be very generous about how these parameters can behave. We're going to allow them to be continuous or discrete, ordinal or categorical. Cplex has some things where it's like auto or a continuous value. So you can have these funny discontinuities where auto has very special meaning and everything else is continuous. You can have parameters that are conditional, where some parameter gets turned on only in the context of some other parameter having a certain value. So our models are going to allow all of this sort of thing. And to establish terminology, I'm going to call full parameter instantiations, which correspond to what we were looking at in the previous slide, an algorithm configuration. And so in the context of the previous couple of talks, for us, the problem of looking at a design space of algorithms given by parameters and finding one that performs well in a distribution is what our literature calls the algorithm configuration problem. So, but here I'm not going to think about solving the configuration problem. I'm just going to think about building an empirical hardness model that performs well as we vary the set of instances and also the set of configurations. So what I'm going to do is vary the set of instances and configurations in my training data. And then at test time, I'm going to consider both instances and configurations that I've never seen before. So that's a pretty hard problem. You can imagine varying either only one or the other. But here I'm going to vary both. And again, we have a giant paper that does a really exhaustive analysis of this. But here are some suggestive pictures to let you know what it looks like. So here again is MIPLib. Here again is the IBM verification data. But now we're looking at every one of these points corresponds to an algorithm that hasn't been seen before in training data, from this fixed space, and also an instance that hasn't been seen before. And what you see is that the pictures are not as pretty as before. We're getting a bigger variation. It's important to look at these root mean squared error numbers because, again, your eye tends to get drawn to outliers in a scatter plot. But we're still getting root mean squared error of less than 1. And bear in mind that if an algorithm made an order of magnitude error in predicting runtime on every instance, it would have a root mean squared error of 1. So this should make you think that on average we're doing considerably better than predicting the order of magnitude. And we have variation across many orders of magnitude here. So again, my hope here is that you're left with the sense that this is possible to do subject to some error. Yeah, Rita.
Does it matter how many learning instances you have seen?
Absolutely, and that's another thing we've studied. In a sense, that's what these previous talks have really focused on. Trying to establish how many instances you need. We don't know the pseudo dimension of these problems, so I can't tell you something analytic about it. But typically what we do is we just overdo it. We try to just gather a lot of data. Computers are cheap, and grad students are expensive. So we just try to gather a lot of data and not have to think about it too hard. Yeah.
Perhaps you covered this before, but by SAT, do you mean finding a satisfiable assignment?
Yes. So the SAT problem I'm going to talk about is, here's a SAT formula, find me some satisfying assignment. And the MIP problem I'm looking at is, here's a mixed integer program, find me the optimal solution and prove that it's optimal.
And you're given that there is a satisfying assignment?
No, so you might also be asked to prove that there does not exist a satisfying assignment. I don't think any of the distributions that I'm looking at here is purely satisfiable, although there are some distributions we've studied that are. Okay, so that's what I wanted to say about empirical hardness models. I just really want to tell you, we've got this crazy thing. We can use machine learning to make pretty statistically robust predictions of how some black box algorithm is going to work on some realistic family of NP-complete problems. What can we then do with that if we have such a thing? Well, I guess I told you learning as a tool for algorithm design and beyond worst case analysis. So here's the part where I want to tell you how we can use this thing as a tool for algorithm design. And the first sense in which we can use it is for this problem that I'm calling algorithm configuration. Let me say, over the last decades, but continuing over the last 10 or 15 years, Moore's law has just been marching on, right? This is the Moore's law graph. And what this means is that we have, even though your laptop hasn't really gotten any faster, this is your laptop. This is the clock speed of a computer that you can buy. That's kind of flatlined since about 2000. But the computers in the data center have just more and more transistors, and so for the same cost. And so what that means is you're able to do crazy things on clusters of computers that just wouldn't have made sense to do 10 or 15 years ago. I think that's indeed where the deep learning kind of breakthrough has come in. Deep learning can really be understood as saying, look, machine learning used to say, come up with your features very carefully, thinking about it as an expert, tune your model family by hand, tune your hyperparameters with little experiments. And really, the deep learning people said, computers have gotten fast enough that we can actually do something crazy here. We can have really highly parameterized models that rely very little on expert knowledge. They're deep in the sense of having many layers of parameters that depend on previous parameters. we can survive having lots of data as long as we regularize appropriately. And then we can just search this crazy thing using all of these transistors that are now at our disposal. We can spend days and days running on clusters of GPUs, and we can actually fit models. And there's a little bit of nice theory that's happened in deep learning, but I think even the kind of people working in this area will argue that this is mostly a story about computational power. That being the case, you might wonder, what does that mean for us if we study optimization? And I would argue that there's a kind of analogous deep optimization program that one can follow. So the way people in the kind of AI community think about attacking some problem domain that is important to attack is, an expert comes up with a heuristic algorithm based on all kinds of knowledge of heuristics, things that have worked in the past, and then they iteratively do small experiments to improve the design. They kind of iterate in this way until the conference deadline, and then they submit what they've got, and that's their algorithm. And instead, what we've been advocating for some time now is what you might call deep optimization, because it looks very much like deep learning. So we could instead think of our algorithm design spaces as being very highly parameterized by all of the heuristic design choices that you might have ever thought of making. And they can be deep in the sense that there can be many levels of parameters in the algorithms. There could be parameters about which algorithm family do you use, and then which algorithm in the family do you use conditional on the algorithm, and then which sub-heuristics given the algorithm, and which parameters of those sub-heuristics. So we've really come up with some algorithm design spaces that are 4 or 5 levels deep in this sense.
Wait, is it the same kind of deep? It's not.
I would say
deep means parameters depending. You define new parameters depending on what.
That's what I'm saying, exactly.
That's what you do.
Right. So the example that I just gave you of an algorithm family, and then an algorithm, and then a heuristic of that algorithm, and then a parameter of that heuristic, each of those parameters has meaning based on the parameters that come before. Now, the sense in which it's different is we're not having these things be identified by the model, right? We're coming up with this ourselves. So that is the sense in which it's different, and I don't want to gloss over that difference. But the sense in which it's similar, really, is, again, we use a lot of data, and again, we resolve this space by leveraging this large amount of computation. I mean, in the end, we want to find an algorithm in this space that performs well, rather than finding a model that predicts well. I mean, the underlying problem is a little bit different. And you could indeed wonder, to what extent can you actually do representation learning in this domain? There might be ways of pushing the analogy further. But I think what's similar is that people 10 or 15 years ago thought that it just made absolutely no sense to statistically study Cplex's design space by looking at terrible parameter configurations and seeing how they are and finding gradients. And this has become possible to do sort of for the same reasons.
So you would do like empirical gradient? You would do like numerical gradient?
Let me tell you a little bit about what we would do. Some methods are based on gradients and some are not. But in one way or another, you want to search this space to find minima in the space. So indeed, the algorithm configuration problem is the problem of answering your question, of saying, how do I want to search this space? And as an aside, I want to say I think this is a pretty interesting algorithms problem that should interest all of you. So our input is all of the parameters that encode the design choice that my algorithm designer came up with. And what I want to do is basically automated experiment design. So I want to find some parameter configuration with good performance by making black box calls to this parameter space and then making observations at any point that I choose to observe. This is complicated because the design dimensions can be, in some cases, continuous, and in other cases, not continuous. There's another design dimension, which is which instance do I choose to test on, where my objective function cares about some aggregation across all of the instances. But I can, for example, choose to do a blocked experiment design where I keep looking at the same instance over and over again to reduce variance. My objective function to be minimized is something like the average runtime. And that's interesting because the cost of evaluating a given point also depends on the average runtime. So if I look at a really good point, it's very cheap for me to make an observation. If I look at a terrible point, it's very expensive for me to make an observation. So I don't have a uniform cost structure where I'm going to be limited to some finite number of points, but instead I have a time budget. And in fact, I can even reason, be kind of strategic about that time budget. So I can say, I'm going to choose to evaluate this particular point, but only for a second. And if nothing comes back after a second, I will have learned a bound. And if it's below a second, great, I've learned something good because I'm trying to minimize something. And that number a second, of course, I actually get to reason about that. My algorithm can be dynamic about choosing what that number should be. So this whole kind of black box optimization problem I think is a very interesting one. There's, I think, room for some deep theory in thinking about this. And there's a little bit of theory already drawing on kind of bandit ideas, but I think a lot more can be done. So let me tell you the current methods that we use, which are based on this idea of the fact that it's possible to do runtime modeling. This picture that I'm going to show you is based on Gaussian processes because in one dimension, Gaussian processes give it a prettier picture, but we actually use random forests. So here's the real problem. So let's say this blue line here is the actual algorithm runtime that across the parameter space. So the x-axis here is different parameters. The y-axis is how expensive is the algorithm given those parameters. And what I want to do is find the best algorithm. And so I want to minimize this blue function. But I don't get to see the blue function. This is something I only get to have kind of Oracle access to by doing a run. And so each of these circles is a place where I've previously done a run. And the solid black line is the mean of a Gaussian process across these samples. So you can see it's confident where it's seen a sample, and it has error bars, which are these dashed lines, away from places where it's seen a sample.
How do the instances, this graph is...
So this graph, think of this as the average across instances.
Average.
Because my objective function is going to be the average across instances. So I'm going to need to, again, this is kind of a cartoon. The real algorithm has to be more complicated and has too many dimensions to put on a slide. But think about this as an average across instances. And so then I'm going to have an acquisition function. Here the acquisition function is the expected improvement over the best thing that I've seen so far. So right now this is the best thing that I've seen so far. And the expected improvement of every point is saying, conditional on your runtime being better than this, how good do I think you are? And because these are Gaussian processes, there are Gaussians everywhere. So there's always some probability mass kind of out to very low runtimes. So I'm going to show you a video now that shows you how this thing actually runs. So it begins by saying, let me look here. And then it kind of keeps going to the place with the best expected improvement and then updating the model iteratively. And so eventually what we get is a bunch of samples in a place that looks good. And we don't waste our time sampling places that look bad because the error bars in our model tell us that there's nothing worth looking at there. So that's kind of how this approach called Bayesian optimization works. Yeah, Shuchi.
So is there some smoothness assumption that you...
Well, there's a smoothness assumption to the Gaussian process. As I said, we're using a model, random forests, that doesn't make a smoothness assumption. It models the space as being piecewise constant. So we have discontinuous jumps. When we have discontinuous parameters, that's a good assumption to make. When I show it to you in one dimension, it looks kind of ridiculous because you just sort of see a staircase. So that's why this example doesn't look like that. But broadly speaking, this is called Bayesian optimization because we have sort of a posterior belief over how good my algorithm is, everywhere in the parameter space, including points that I haven't observed. And then we reason about that distribution to decide how to solve this active learning problem of looking where to go next. The algorithm that we've actually proposed in our group is called sequential model-based algorithm configuration. And it's essentially the same sort of idea based on a random forest model and thinking about problems like the one you raised about how do we actually think about which instances to pick, how do we think about this runtime capping problem. So I'm not going to go through the details of how this thing works, but essentially it's kind of like what you would expect given what I've told you so far. And let me just say, we've produced this thing as open source software. We've released it publicly since, I think, maybe the past 5 years. And it's been really widely used, both by us and by others, to have really practical impacts in a lot of different problems. So here's just some examples of places by us and by others where this approach has been used to tune algorithms and achieve better performance than people were able to achieve by hand. So that's what I want to say about configuration. Let me say something about another idea called algorithm portfolios. And this is typically what we mean when we say algorithm selection. We mean, even when I get down to sort of good SAT solvers that people have bothered to identify by hand, it's typically the case that there isn't a best one. That different solvers work well on different instances. And this gets to the question that Uri was asking in the last talk. Maybe rather than just running, having to commit in advance to one thing that has the best average performance across my distribution, I should instead kind of take a portfolio approach where if I'm able to predict runtimes accurately, I could predict runtimes for every one of these different solvers and run the one that was predicted to be best. Or alternately, if I have a lot of parallel computation available to me, maybe I would just run a set of solvers that look good in parallel, and then that whole process would terminate as soon as the first of them terminated. So back in 2003, we made a SAT solver called SATzilla, which is graphically depicted here. And it basically has done really well in the SAT community. So the SAT community has these SAT competitions, and we just basically destroyed SAT competitions by taking other people's SAT solvers, which I have to say I didn't even deeply understand. We just basically took kind of machine learning and wrapped it around other people's stuff, telling them that this is what we were doing. And we just kept winning the competitions because it was, because portfolios are a really good idea, right? That's why you should all buy an index fund. Like it's just much better than, trying to just find one thing that you think is going to work really well.
So,
and basically, in the competitions, we just did spectacularly well until they decided they were pissed off at us and they banned portfolios.
How did they enforce that, by the way?
Well,
How do you define
I guess there's no academic glory to be had by breaking the rules of the competition and then telling them that you did that. So that's kind of how they enforce it. Yeah.
This is, in machine learning, ensemble methods are...
It's a lot like an ensemble method. The way that it's different is that if you think about something like boosting, every element in the ensemble gets evaluated and then you vote. With a portfolio, you don't want to get the measurements from the guys that are slow. That's the whole problem. So you kind of only want to run one of them or you've paid far too much. But actually, the second paper that I wrote on this topic was called Boosting as a Metaphor for Algorithm Design. So I think indeed the connection goes pretty deep, but it's not as direct as you might think.
It's not direct, correct.
Avram.
Just to be sure, so what you're doing here is you're given the instance, you spend a little bit of time to evaluate the features. That should hopefully not take too much time.
Right, and you pay that up front, so that you throw that time away.
Use that to choose one algorithm,
yes.
And then just go with that.
That's right. Okay. When we really want to win the competition, we have a couple of other sort of complicated engineering ideas that make things work a little bit better. But for this purpose, that's not interesting. So let's just say that's what we do.
So what's here, what Avram was saying, there's another waste of time, which is evaluating on the, so you
the features.
measure the features, now you have the features, now you want to evaluate
the model.
The model.
That's correct. Typically the model's much cheaper to evaluate than the features, so I think to a first order, Avram's story was right, but yes, we have to pay all this cost.
When I have to pick between different machine learning tools, I want a machine learning tool that is fast in prediction time.
Yes, which typically they are. In particular, random forests are basically a tree data structure where you look up the point you want to find, so they're very fast at evaluation time. Again, I think this is interesting. Just kind of as a general recipe, more than analyzing exactly how fast were we on some distribution. So I kind of just want to leave you with this idea that we can, this again has worked very generally across different domains. Something I think that's really enticing about it is it shows that there are some solvers that people had called uncompetitive that used to be great like a decade ago, and they've really fallen out of favor. And our analysis has shown that they actually, they're really great to have in a portfolio because on like 10% of the instances, they're really uncorrelated and they're really fast and they're utterly terrible the rest of the time, but we don't care if they're terrible because we can predict they're terrible. Actually, in some of our most recent work, we've thought about how to use ideas from cooperative game theory to use the Shapley value to say how valuable is each solver to a portfolio. And we want to argue that's actually how you should really think about the value of an algorithm in the context of all the other algorithms rather than just in this kind of standalone way.
So, question?
Yeah.
So that seems also like a way of feature selection. This.
Well, it's not features in the sense that I had before, but I think actually even the thing I'm about to say next maybe will feel even more like that to you. So let me say the next thing. So everything I've said, you might notice some sort of cognitive dissonance between my first application and my second one, right? With configuration, I said, let's do this automated design where we find some point in the design space that maybe would be surprising to a practitioner. And then for portfolios, I said, I'm given some small set of known to be good algorithms, and I want to choose among them in some good way. You might think, why did you give up on this automated algorithm design idea that you had? And so we have an approach called Hydra, which is a marriage of these two ideas. And basically it says, let's imagine that I have some enormous design space, and I want to ultimately come up with not one good algorithm, but a portfolio that works well as a portfolio from this design space. And basically this works really well. Essentially what it does is we change the performance metric that we're optimizing for iteratively. So this is you can think of this as a submodular optimization problem where I start out saying, what's the best thing to add to a portfolio of size 0? That's the thing I would have picked in the first instance. Then when I'm looking for the second algorithm to add, I say, I already know that I've got the first guy, so I don't care if my second algorithm is worse than the first guy, because I'll just use the first guy. But I care about him being better sometimes. And so I say, who is the algorithm that makes the biggest marginal contribution to my existing portfolio? And that's my new objective function. So every time it's worse than the portfolio, I'm just going to score it as the portfolio. I try to maximize that. I produce a second algorithm, and I can iterate this as many times as I like until diminishing marginal returns means that I just stop finding anything. Let me give you
So, this is really the analog of deep learning, right? So now you can propagate back which features were good, right? Or which combinations of features.
I'd love to talk to you about that more because I still think we don't do nearly as much with features as we might. So let me take that offline. But I think this is at least taking steps in that direction, yeah.
Right. That would be an obvious next step, right?
I think that's right, yeah.
Like send the feedback back to the features, right? And eliminate features or take combinations.
It would be very nice to see that working, yeah.
Question about Satzilla. So how large were these feature vectors that you computed from the SAT solvers?
Typically something on the order of like 100 plus or minus 50, something like that.
Did that evolve over the computations, or was it?
Yeah, it evolved it just strictly grew. Random forests are a feature selection method. If there's a feature that's not helping, they just don't choose it. So they deal very robustly with lots of useless features. So every time we read a new theory paper, or somebody came up to us after a talk with a good idea, we would add those to the set of feature feature vector.
And did you go back and look at them and try to understand why certain?
Yes, if time permits, which I'm not sure that it will, I'll tell you a bit at the end about what we can do in that vein. But that's the beyond worst case analysis part of my promise to you, which I think I will not satisfy. Okay, so I think we'll get just to the very beginning of that. But what's that?
This afternoon we'll have.
Yeah, indeed. We can talk about it in the discussion sections afterwards. So let me tell you, this actually is going to be pretty quick, but I just want to show you that this all works. So you already heard earlier this morning about the FCC's spectrum repacking task that they're currently doing. I turn out to have led the team that actually designed the algorithm that is being used in this auction to solve this graph coloring problem that the reverse auction repeatedly needs to solve. A quick shout out to all of the people, both at UBC, at Auctionomics, which is an auction consulting company, and the FCC, who made this work possible. This was a giant project, so thanks to all of these people. Basically, the FCC designed a very complicated auction simulator, which produced many instances from different simulation assumptions and different random runs of the simulator that were kind of realistic problems that might be encountered in an auction. And we don't know everything about the auction, but we know many of the parameters. We know the different clearing targets that could be possible. We know the populations that stations serve, so we know a decent valuation model for the stations. And we know the actual underlying constraint network that really will be used in the real auction because we know the actual television stations in the United States. So these simulations are not perfect. And in fact, I can't tell you how imperfect they are because the auction, which is currently going on right now, it's actually secret. I personally am not allowed to know the results of how my solver is doing. But we do know that it's running on the same constraint network. And 2 years after it ends, I'll get to look at the data along with all of you, and we can find out how we did. But basically, these graph coloring problems, we have to solve a graph coloring problem every time some station is being offered a price movement. Right? Every time I go to one station and I say, I previously made you some offer, now I want to make you a lower offer, that corresponds to a graph coloring problem. And because I have to do this in sequence, and there's like 3,000 stations, the FCC is willing for us to have a 1-minute cutoff in each of these graph coloring problems. And it's okay if we don't solve all of the problems. Every time I fail to solve a problem, I have to be conservative and just not let the price move. But that usually means that I'm leaving money on the table. And so the goal is to leave as little money on the table as possible. So when I first got involved in the project, the FCC was looking at mixed integer programming solutions to this problem. I'm not allowed to show you exactly what they were using, but here are Cplex and Gurobi running on all of our data. Now I'm going to be, again, using machine learning methods here, so I'm going to be training my methods on a training set and then evaluating them on a test set. So all of my graphs here are test set performance. I'm not actually training anything about Cplex and Gurobi, but nevertheless, this is my test set. So what I'm showing you here is a cumulative, empirical cumulative distribution that says, within this amount of time, what fraction of my test set instances got solved. And so what I'd like to see is that this thing goes right up to 1 and stays there. That would mean I solved everything really, really fast. And what you can see is sort of the opposite thing, where it stays really close to the bottom until the end. This is my 1-minute cutoff. And so you can see within the minute, Gurobi is solving about 10% of the instances, and Cplex is solving about 1/4 of the instances. And that's really, really terrible. You couldn't run an auction this way, because that means 1/4 of the price movements are possible to make. That means most people are not even getting, they're stuck at the reserve prices. Really, really terrible. So the auction would not have gone forward with solver performance like this. Our first kind of insight was that this looked a lot more like a SAT problem to us than like a MIP problem, because it's graph coloring. There's no real values. There's no objective function. So we took just everything from the SAT competition, and we ran everything. And here's how all the different SAT solvers did. A lot better. Here's Cplex and Gurobi for comparison. The best thing was the local search algorithm, which is not too surprising, because most of our problems are satisfiable. And it doesn't matter that much if we prove unsatisfiability. But it's still not good enough. Like, this is maybe 2/3 of the instances solved. That still leaves a ton of money on the table. The next thing we did was we configured all of these solvers to see how they did using SMAC. That was a lot of work, but I'm not going to tell you about it. I'm just going to show you the best thing that happened. So here's CLASP, which you can see is just in the sea of different solvers here. It's not particularly fantastic. But CLASP was designed by its authors to be really amenable to this kind of deep optimization approach. And so you can see after configuration, we end up with a CLASP solver which is designed for the US interference graph of the graph coloring problem. And it turns out to be fantastic on that graph. So we're getting up now to sort of 75% of the instances. Then we basically used Hydra. So we then tried to build an algorithm portfolio of many different solvers, starting with this CLASP configuration that would do as well as possible, along with a lot of other algorithm sort of problem-specific ideas that we introduced as new parameters, which I don't have time to tell you about. But here's the upshot. We ended up with an 8-algorithm portfolio of all of these different algorithms. The red line is the performance of the 8 algorithms running in parallel. And you can see it's fantastically better than it would have been otherwise. So I'm not going to be able to tell you about my last section, but let me spend sort of 30 seconds telling you what you're missing. So what I would have told you about is, OK, if I've got a model that makes good predictions, you can think about this model as a starting point for theoretic analysis. You can actually look at which features are driving the model, try to take them apart and say, what can I learn about what's important to this solver's performance in this setting by looking at how the model works. And most ridiculously, I would have told you about the fact that we can actually directly predict satisfiability status on uniform random 3-SAT problems at the phase transition. We can, that prediction, I'm just going to skip ahead here. So many fun things you're missing. But this ridiculously simple model, which is a decision tree with 2 variables in it, is able to predict at about 70% accuracy how well a solver will do on uniform random 3-SAT at the phase transition, ranging from problems that are super, super simple to problems that take about a day to run, and trained only on these ones. And I think this might be an interesting starting point for theoretical analysis, because this model is so simple you can actually think about it. It involves, the really determinative feature in it is the coefficient of variation in the slack vector of the LP relaxation. So I'm happy to talk about that more afterwards, but I wanted just to show you this at least as a cartoon to give you a sense of what might this look like as a jumping off point for theory. So with that, thanks for your attention, and I'm happy to chat over lunch.
After lunch too, so I guess let's just all go eat.
I think that's the right choice. Yeah.
Let's be back at 2 for the.
But I wonder if Avram wants to say something, or if I want to say something about how the breakouts are going to work. So we're going to have 3 different breakout sessions after lunch. They are going to be, I guess I'm going to be leading one, which is the easiest one for me to describe because I'm leading it, which is going to be on kind of data-driven approaches for algorithm analysis, so for algorithm design. So my hope is that people both from theoretical perspectives and kind of statistical perspectives will have a conversation about what it makes sense to do algorithm design in ways that are informed directly by real data. Avram is going to be chairing a second session, which he will tell me what it's called.
Let's see. So Holger agreed to join me, and we'll talk about kind of properties of real-world instances, and what could we try to hope to. Are there sort of properties that seem to make algorithms work well, and we could maybe try to develop theory about what do people see, and what might be some things we might in terms of assumptions that one might try to write down and hope to prove some theorems on.
And while you're at it, why don't you tell us also about the third one?
Our third one will be Sanjeev.
You slipped away, which is why you have to tell us about it.
Well, which you will find out at 2 o'clock.
So I think our aim with Sanjeev's one was that it was going to be relatively more theoretically oriented because these two were relatively less theoretically oriented, and it would also have more of a learning flavor. And I don't remember exactly the mission statement that he picked, if indeed he had settled on it. The idea is going to be that we're going to have 3 different locations. We'll have signs telling you where they are, but we'll have 3 different locations. I mean, maybe we should all meet at 2. Yeah. We'll sort of dispatch everybody and figure out where to go. We're going to have 3 different locations. You can come and go between the different sessions. The breakout will last for an hour and a half. Then we'll have a talk by an hour and 20 minutes. Don't take too long. Then we'll have a talk by Shafi, I think. And then we will have sort of the 3 groups come together, and the chairs will sort of report back what you heard in the groups so we can all hear what happened. So see you after lunch. Thanks.